Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my x86 operating system written in Rust. It's currently, it like boots, it does the memory allocation, it has async await support, it's got serial logging, VGA logging, unit testing, clock support, PCI Ethernet. And we've kind of got all of the pieces there now to start doing actual interaction with the outside world. And so the goal for today is to correctly parse and maybe send back UDP packets from the outside world. So the way this works right now is QEMU implements this user mode networking, which basically means it like opens up some ports on the local host and it forwards the connections from that port on localhost to a port in the guest. So what we have set up from last stream is if I boot my OS and then I try to like use netcat to just like send some shit over UDP, I get something in here, which is notably not what I'm sending, right? That's an important piece here. And if we look at the CRC of the Ethernet frame, we do get the same thing. If we calculate it ourselves, we get 1726 AC72, but in reverse, that's 1726 AC72, which is what's in the frame. So it's just some like big endian, little endian differences there. And yeah, what we worked on yesterday was, not yesterday, sorry, 2 days ago, was trying to figure out like what this packet that we're getting is. And what we deduced was that it's an ARP request, where ARP is a address resolution protocol. Hold on, I'm trying to find a window that I can open to search this on the browser. One sec. ARP protocol. So this guy is basically just a way for the network to like determine who has what Ethernet MAC address, right? Because my Ethernet driver, he's got a MAC address. Where is it? It is a MAC address. Maybe I'm not writing it down somewhere, but yeah, oh, here. It's a MAC address 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. And QEMU, what it knows is it knows that it's trying to forward to a specific IP. And so it doesn't know what that IP is or where it lives, but it might ask the network. It broadcasts a packet to all Ethernet devices. It just like sticks it on the wire, and all network cards that are physically connected there are going to get that packet, and they're going to read it. And what the packet's going to say is it's going to say, who of you many people in this world, there's only one of these many people, but it's going to ask, who of you owns this IP? And this IP is kind of like a lie, 127.0.0.1. And what we can do is we can say like, hey, I have IP 127.0.0.1. Just let me know, like, here's my MAC address. And what that does is it lets the system to know if it's trying to route a packet to that IP. It can then physically send that packet out with the MAC address of the network card, and the network card will then go like, oh, that's for me. Let me eat that. Num 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 num. Right? So the problem is we don't have that protocol implemented. So what we suspect is we've kind of like deduced last stream without really reading too much. But there is this packet here that looks like a hardware type, which is just Ethernet, right? Easy, that's going to be the same as what we receive. There's a protocol type, which is just going to be IPv4 because we're not using IPv6 or anything. Hardware address length and protocol address length. This is 6 for a MAC address and 4 for an IP. Those are fixed. Operation, we think, is there's a request and a reply. And the request and the reply still have like the same stuff in there. So all we have to do is make a reply where we fill in our sender hardware address and our sender protocol address. So this is going to be the IP that was requested. This is going to be the MAC address of our network card. And this is going to be who we're sending back to. And so where we got there is like, in order to send this packet though, we need to support Ethernet frame packing, which we don't right now. Which is basically like you make an Ethernet frame that the network card will read and determine if the packet is for them, and maybe like give you a pointer to all of this stuff and know how to parse it, etc., etc. And what it gets is like a MAC address, destination, a MAC source. So I say like, hey, this is from me to you. This is optional, so we're skipping it for now. We have Ethernet type, which basically says like, what protocol am I speaking? So this is going to have to say ARP in here. We're going to put in the rule for ARP. The payload, which is easy, that's just like the ARP packet. And then here's where we kind of got a little hung up yesterday, or 2 days ago, was this like CRC. And we spent a lot of time here, and we kind of figured out eventually that we have CRC FCS, I think, is going to be frame check sequence. What we found out eventually is we eventually found this HDLC implementation of CRC, where CRC is this like way that we can we can like take a stream of data and checksum it and basically make sure that like there's a very low probability that what we calculate is going to be the same as what we get, what you sent us, unless we got the exact right data. And so we kind of struggled with this. And off stream, at the end of last stream, we were testing with this like CRC Rust library. And we found the right parameters for this CRC algorithm. And once we got there, I kind of figured off stream it would be kind of fun to just like go through and go back and see if I could like really understand CRC and get into it myself. So what we have in here is there's like this online document called A Painless Guide to CRC Error Detection Algorithms, and this is like a really good walkthrough of CRC, and it actually kind of explains why I was struggling so much. This is actually like kind of complex, even though the actual algorithm itself is quite simple. Like how we get there and what it means and what's going on is like not trivial to understand. So this is a good read if you're curious. And basically all it is there's this like polynomial. They kind of model this as like x to the 32 plus x to the 31 plus x to the 30. And each of these has a binary prefix, 0 or 1. And so each bit in my 32-bit number is representing like one part of the polynomial. And what they're basically saying is if I like divide these polynomials, I'm going to end up with this thing where x to the 32 is only going to match with x to the 32, and it's always going to be 0 or 1. And so like you go through all this math and you basically get to the point where you're just saying, this is an XOR, essentially. So we have this polynomial that's like defined as part of the Ethernet CRC check. And it's like a specifically picked polynomial that has like some properties. I didn't really get into that. And this is like agreed on. And so basically what I do is I say like, for each bit in the entire sequence, so we iterate over bytes, and then for each byte we iterate over bits, and we basically just say like, I'm going to shift that bit in and divide it by the polynomial if it's 1. Otherwise, I do nothing. And this is like kind of like a pseudo for long division, or like an approximation of long division, or not approximation, it's just like a weird way of doing long division with this scheme. And when we get to the end of it, there's like some extra parameters. It means like we're right shifting instead of left shifting, because like that is how it works out for Ethernet transmission order. It just like makes more sense that way. And which means that like the chosen polynomial has to be reversed. And then at the end, we XOR out the bits with 0xFFFFFFFF, and we start with 0xFFFFFFFF. But other than that, it's actually pretty straightforward. And so I wrote a couple tests, and this still works. Bing, bang, boom. Pretty happy. Yeah, so that's kind of where we're at. And so today we're going to, now that we like know that we can generate this CRC, we're going to try to like put that to work and generate Ethernet packets that are discoverable. The other piece of info that I found out off stream is in QEMU, there's this filter dump parameter. Filter dump, I lost it. That says I'm going to dump the network traffic that I see within the virtual machine, and I'm just going to like put that in a format that you can open it and browse it. So let's just pull this guy in, and we'll say we'll open this QEMU wrapper, and I think that if I just say filter dump and I say set my net device to N0, or maybe ID to N0, I don't know, they're kind of the same, And I think that's probably it. Just fixing up some upstream things. So cargo run. What I should see now is, oops, parameter file is missing. So let's just put in file equals dump, network dump or something. If we run this now, and I actually run, like dump, punch in a packet, if I now look at the network dump that we just generated, we actually see this broadcast packet sent in. And this matches what we see, right? We get in a frame with Mac FFFFF0, source Mac 525A, 5255A, and hopefully if we find this, we can actually see this data. So Ethernet parameters, so we have broadcast, right? FFFFFF 5255OA000202. That matches. The type is ARP, which matches what we've discovered. And the ARP request is also matching what we've discovered. So we have hardware address length 6, protocol 4, opcode 1, sender MAC, sender IP. These all match what we've printed here, which is pretty cool because we kind of like discovered that last stream without the use of Wireshark. So what I'm hoping to do is use these tools to figure out how to send Ethernet frames back, finish our ARP, like generate an ARP response, and hopefully that'll be enough to like kick QEMU into a state where it's ready to keep going and send the actual UDP packet that we're punching in here. That's the goal. So let's just get into it. So this is done. And let's implement sending of Ethernet frames. So we'll kill Wireshark and we'll get back into our code base. And for now, we're kind of just punching everything into main as we do our experimentation. And then eventually this will move into like its own correct external modules, whatever. But for now, we're just kind of doing it here. So I think all we have to do is we need to generate an ARP response, which we had like kind of set up last stream, where we say like we take the request here and we copy it, and then we just swap the sender and target addresses. And all we should have to do now is like inject this into a payload of an Ethernet frame. So let's kind of look at what generating Ethernet frame would be like. So we can say generate frame, or maybe generate, and this will return an Ethernet frame, right? And in here, we're going to take in some parameters, right? So we're just going to take in these parameters that we care about here. So we're going to take in struct Ethernet frame generated Ethernet frame params. And maybe this shouldn't live in here because this is kind of like a reference view into an Ethernet frame. But what actually makes more sense here is for us to just like return like a bunch of bytes, right? If we return a bunch of bytes, then that's easy to just like punch into wherever we want to go. So let's do it that way. So we'll make just a free function that's like generate Ethernet frame. And he's going to take in params that are Ethernet frame params, right? And he's going to return a vector U8. So just a byte array. Easy peasy. We need to include vec. So somewhere we just have to say we want to use vec and vec. Okay. And probably the parameters are going to have dest mac, which is going to be a U86. Source mac also going to be a U86 because these are 6-byte MAC addresses. Ether type is going to be a U16, right? Because these guys are just like full-on numbers like this. What else do we have? Payload. And this is just going to be a... we'll copy out of this for now, but maybe there's a way to like inject a owned buffer so that it's easy to work with, etc. But for now, we'll do this. And here we go. So what are we going to do here? First, we're going to allocate a buffer that's at least 64. So we're going to say, or actually we can kind of calculate the full length of this up front. We can say length is destmac 6 for the destmac, or params.destmac.len. Size, I guess we want the size in memory. We can just kind of add up the size in memory of all of these things. Maybe. So we'll say params destmac, which is like, I think, core mem size of val. Right? So we take in the destmac, and we just do this a few times. So we say that we add on the size of the source mac, and we add on the size of the ether type, and we add on the size of the payload. And then we need +4 for the CRC, right? And so then we can start making a vector. So we can say, let our output is a vector with capacity length. And then we return ret. Right. And then what we can start doing is we can just start punching stuff in. So we can say ret.extend from slice params destmac. And we need the source mac. And then we need the ether type, so we can say we want to once again extend from slice because we need to convert the ether type into a big Indian number. So we say params ether type 2be bytes, right? And then we extend the payload, which is just params payload. Right, we're pretty close here. And the last thing is to generate the CRC. So we say ret extend from slice. We calculate the CRC. So we just take in the current ret. And 2 BE bytes. Okay, so this should actually, that should be it, right? All we've done is we've just generated this guy. And that should be enough. So let's see what happens if we try to generate an Ethernet frame like this and send it. So we can say let response frame is the generate Ethernet frame with Ethernet frame params. Destmac is just going to be the incoming frame source mac, right? As a reference? No. This has to be try into because we have a slice of the source mac coming out of the Ethernet frame. But we expect a U86. So maybe actually here, no, we can't like size the slice, I don't think. I think like this won't compile. Yeah, we can't just say like this is gonna be a reference of a 6-byte U8 array because it's not. It's a reference to a longer byte array, and we're taking a 6-byte subslice of it. So unfortunately, I think that means that we need to do some like runtime conversion here. So we just say like, we're going to like take the slice, we're going to try to convert it into a 6-byte array. And if we fail, that's like a programmer error. We're going to just say like invalid length for destmac for dest mac. Right? And we're going to do the same for source mac, except we're going to replace the dest with the source with the dest, right? We're swapping them. Ether type is going to be ARP. So for now, we're just going to punch this in manually, but eventually we should replace this with a proper type internally. So let's just, for now, we'll punch this in, and we'll just say, fix me enum with 2int or something, right? This should be like a named thing. We should just write ARP here, and then internally it will convert that into the number it needs to. And we're using payload. So the payload should just be the ARP response. I think the ARP response just has the thing built in. So we'll just say ARP response dot packet. Okay. And now we can just send the response frame, maybe. And if that works, I'm going to be very surprised and impressed. And we'll say failed to write our response. This will also have to eventually become a like proper return type. So what I'm actually going to do is I'm going to say unwrap here, because using unwrap is like a way that I flagged to myself that this shouldn't actually, this is not like the real code. This is what I will provide later. And unfortunately we can't await this. So we might actually have to make, what we do is when we read a packet from the Ethernet driver, we like call this function on it. And we call this function on it because we want to be able to free the packet after this function's done. So we actually can't really just, this allows it to be like 0 copy as well, which is pretty nice. So we can just say like, here is a reference to the bytes that the network card wrote directly, and we promise you that while this function is running, that will be valid. And if you want it later, you want to stash it to do something with it later, you can copy it yourself, but we're not like forcing a copy on you. You can do whatever the fuck you want. But what that means is that we can't do like async functions in here like we're trying to do here. And so what we could do is we can just say from our driver, instead of you passing in like giving us a function that takes U8, you're going to give us a function that generates a future. And that just means that all we have to do now in here is we just have to type in like async here. I think. We'll find out. Found async block. So let's see what it's bitching about. Expected future found async block. Oh, because it can't actually... Oh no, that should work. So why... What doesn't it like here? So first of all, this probably has to be propagated down to the inner value, the inner function. So we'll just copy this over here. So we'll just say comes here, this returns a future, and this guy says future is core future with an output of nothing. Okay? So now that they're happier here, but this is still broken. So I don't understand why async block does not implement future's future output. Expected opaque type impl futures output equals this. Found async block. So let's see if we can figure out why that is. Found async block expected impl future Rust. Because I thought that those should be the same. Rust async block to future. I don't understand. Let's see if I just type return, that does give me a more useful error. Found async block. Rust async block implement future. Yeah, I'm positive this is supposed to work, but I must be missing something. Async block is impl future output the real return of the function body. Right, like if this works, let's look at like their type signature for this guy. So this is the Tokyo runtime, I bet. And they probably have function block on, right? And what does he take in? He takes in a future, right? Where F implements core future. And so, like, why does this not work? Maybe my future, oh, maybe this needs to be two individual futures here. Maybe they're like saying like the type of sleep needs to match the type of on read, and those don't match. So let's just take out this sleep shit and see if that fixes anything. No. But we're getting closer. Okay, so that actually fixed that error, but we're now in a situation where we can't actually return, we can't use this packet inside the async block because it might outlive it. What if I async move? Okay. Fuck, that's like annoying. So the problem is that we're using self RTL 8139 in the async block. And that's now getting moved in, even though it shouldn't, right? But how do I say this? If we don't move, then the packet here that we pass in doesn't live long enough. But we might actually be able to like force this into here, where if we like give this a lifetime, we might be able to attach that lifetime here. So let's try that and see if that helps. Let us see. So we need to do the same thing here. And we are maybe close. Cargo check. Let's see what it doesn't like. So it's saying that we have a lifetime here that we have to maybe attach to A as well. Okay, look at that. We're maybe getting a little close here. So we're saying that all of these guys need to live long enough. So now he doesn't like this because argument requires that V is borrowed for the lifetime of A, but V is dropped. Fuck. So the problem is that we are attaching the lifetime to the lifetime of like my own struct, and now that's no longer true. So let's go back to not attaching that lifetime to self and see what it's complaining about. On read requires that one must outlive A. Why? Why? Oh, but we might be able to say that the B is greater than A. Oh, okay. So that's maybe close. So we say that like we outlive this data, and that's okay. We will just manually flag that to you. God, this is the part that sucks most about Rust. I think that like lifetimes are like the hardest part of this language. So now we're just back in the same situation where yeah, we're just in the same situation where it thinks that these lifetimes are tied together when they shouldn't be. Fuck. It seems like the lifetime system should allow us to specify what we want in some way here. Right? We should be able to tell it that what we pass in is the same lifetime as what we get out. And I'm just missing somewhere that I need to like correctly handle that. So let's try looking at this again. So why does this think that the argument requires that 1 must outlive A? So it thinks that the structure that we're running from, our class, must outlive the data. And it does, because the data is dropped here. So what does it think 1 is? It thinks that this is lifetime 1 and this is lifetime A. And it thinks that argument requires that 1 must outlive A. And it does. Right? That's what I'm confused about. Is like it very, very clearly does. So if I do this now, again, and I say we're going to tie these lifetimes together, it's going to say that borrowed value does not live long enough. So it thinks that oh, okay, wait, we're actually close. So the problem is that this doesn't live long enough, but I think that we can use a different lifetime in this outer version of the function. And okay, so what doesn't it like? What doesn't it not like? Cargo check. Looking again, so it's saying that lifetime A is declined here, the binding V is declined here, V is dropped down here, but that shouldn't matter because this should be just done before that. Oi, oi, oi. So it's something about this inner version as we pass it on. Come on, man. I hate this. We're so close. So I think here we don't have to define anything. V is dropped here while still borrowed. So I don't understand how it's still borrowed at this point. Right? Because here it should be done. We've moved the closure into thing. We get our response back. Let's look at what this guy returns. Maybe this guy needs to return something like this, where like we return like the lifetime of the return, the lifetime of this generated async function needs to match. Oi, oi, oi. Okay, so all of this is too stressful, and I don't want to deal with this. So instead, what I'm going to do is I'm just going to copy the packet. Fuck it, blaze it, you know? Unfortunately, that will make my life easier. So let's just get back to like a clean-ish state here. Oh, actually, we still do need to return the future. And we'll just clone it inside. So we're close. So we return a future here. And this guy also needs to take in a future, or a function that returns a future. So we implement core future. Output is nothing. We await this inside. And here we await here. Everything's chilling. And here we will just copy it. So we will say let packet equals fuck. Okay, we'll go back to doing an async move here. And we'll say that RTL 8139 is a reference to self.rtl8139, a mutable reference even. No, a normal reference, right? And now in here, the reference will get moved in instead of the value, but it doesn't like that. And so let's just double check what lifetimes is bitching about now. And we'll just clone the packet as well. So we'll say let packet equals packet.toVec. And here we pass in a reference. And I think everybody's happy now. Yeah, this compiles. So that's unfortunate, and I would like to get back to this. So I'll put a fix me here and say avoid copying, but types are hard. Okay, so if this all runs now, we should get a network dump where we send our ARP response. But we actually have an unwrap called on a none value. So where the fuck is that? And the only place is here. Unless there's somewhere in like here. It's probably this. So we'll check this one and we'll say failed to get MAC. And we'll see. Yeah, so there is a problem where we were unable to retrieve our own MAC address while we're inside this callback, which is a little annoying. So let's instead go back and we'll say let MAC is equal to self RTL8139 get MAC. It should work up here. And then here, instead of calling get MAC here, we just call MAC. Like this. Cargo run. And let's see if we pass now. And we do. Okay. And so what would be interesting now is if we could look at what we get in our ARP response. We should open Wireshark now and see if we actually send the ARP response, because we should. So let's take a look at StreamOS. Network dump. And we actually don't see any ARP response sent, which is a little weird. So let's see if we can gain some insight here. And I believe that the problem, if I had to guess, we'll say waiting for mutex. And we'll say enter as this. And here we'll print that we've acquired the mutex. And my bet here is that we just never get the mutex. Like this. That is my guess. Because we're in the read callback, which probably has the mutex locked. Just a quick guess. Waiting for mutex, and we see no mutex acquired. So that's a pretty good guess. And what we should actually do is we should release... Does it make sense to release the mutex when we call our read callback? Let's think about that. That means that somebody else could call read at the same time. Is that a problem? I think maybe the fact that we're single-threaded kind of like dodges that. And I think maybe it is reasonable. Okay. So what do we do here? We drop the mutex while we call on read. That's annoying because right now this guy doesn't like know that the mutex exists. He's like this inner guy who just works on the data and expects himself to be locked the whole time. So let's think about this just a little bit. How can we handle this? Maybe instead of this guy running the future... Sorry. Instead of this guy returning a future and that gets run, maybe he returns another future that will get run later after the mutex is unlocked. So we like get in our data packet and then we just return out a new future. So let's see what that looks like. So this guy returns fut. Right, so this guy says let future equals what we get out of this on read. And here you go. Here's the future. And then this guy, he gets the future from this. So he says let future equals this. Then he drops the mutex, which maybe he doesn't have right now. Oh, he does here. So we'll say fut equals this. Sorry. Here, when we get out of the loop, we'll break with this future. Right. And then here we call fut dot await. Okay, so there's all sorts of shit that's going to go wrong here. More lifetime bullshit. So let's take a little peek skis. So I see. So it thinks that the inner value is being used here in some way. And it's actually not, as far as I can tell, right? We call v.read. Oh, he is. Okay. Sorry. Here we go. So we passed like a thing to do later out, and this guy is runnable later. Does this run? So I actually don't understand why this works, because this, oh, it's because we copy the packet here. Okay. So we run our function. This function gets run in the context of the mutex, but all it does is it copies the packet and then defers all of the actual work till later. That works for me. So now I think that if we run netcat, we do see that we like waited for the mutex and we acquired it and we probably sent the response back. So let's look again at this dump. Hey, look at that. Look at that. That's so sick. Okay, so we say who has 127.0.01? Tell 10.0.2.2. And then this guy says, hey, 127.0.01 is at 1234.789 ABC. Now, there's a problem here where the source is broadcast, so we actually need to fix that. Because like we use the input frame that was copied. We use the input frame for our source MAC. But this is actually wrong because the initial request was like a broadcast request. It was sent to everybody. And we're not saying like, hey, I'm from everybody. That's crazy. So what we actually have to do here is do the same thing where we pass in the MAC address here. Try into expect invalid length for source for MAC. Useless conversion. Oh, because this is already a U86. Perfect. 6-byte U8. Hey, Yoshi, what's up? And now if we try this again, and we reopen our thing on Wireshark, come on, baby, let's see it. Okay, so this looks pretty reasonable. So we guessed correctly here, which is pretty cool, that our request requires some form of ARP, right? Because we eventually do get the UDP packet in. Very cool. We have, so the first thing that happens is QEMU says, hey, everybody, who has 127001? And then we respond like, hey, I'm 127001. It's this MAC address. And he goes, all right, then now I can send a UDP packet there. And then we incorrectly try to parse this UDP packet as an ARP request and then just like send some fucking garbage out there. So all we gotta do is fix that now. So that's very cool. Very, very cool. So let's call this done and this done. And this ARP response was finished at around 45 minutes and 30 seconds of stream. Okay, so now let's see if we can like understand this UDP frame that we get in. So the first thing that we need to do here is when we look at our Ethernet frame, what we should do is we should switch behavior based off of the type that we get. So for now, let's just say that we look at the frame ether type. And we'll call that the like ether type. We probably don't have to bind this. We can say match frame ether type. Right? And if we get specifically the ARP type, we'll do this ARP shit, and otherwise we'll do something else. So first, our ether type is in fact a U16 already, so we can say that our ARP type is 08. I think it's 16. No, 02. My guess is 02. We're guessing and checking. 0806. I was wrong. I was hoping that these, I knew it was the second one in the list, but I was hoping that they were sequential, but they're obviously not. So 0806, and if we get 0806, then we do all this Ethernet, this ARP shit, which we should factor out into its own function for at some point, because this is going to be like impossible to read. But instead, we'll do that later. So here we should actually probably say found unknown packet type. This is going to be T, right? And maybe this is a debug, right? Do we think that every time we receive a packet on the network, if we don't handle it because it's not UDP, are we going to log something there that's worth seeing? No, I don't think that's worth talking about. It just means that we don't do anything with it. We just ignore it. Here, I think it's worth doing a debug log of saying parsing ARP packet. And probably the fact that our Wireshark says that we just like parse this UDP packet as an ARP request kind of indicates that there's no sanity checking here. So let's just throw in and like fix me. Should we do some sanity checking on the ARP request? Right, because we're just kind of like blindly parsing and hoping for the best. Okay, let's drop these print lines. We don't care about them anymore. And now we'll just add another handler. But first, let's see if this works. So what we should see is when we run this, if I run with debug logging on, which I just have to enable really quick. Let me find that. Logger init somewhere. Here we go. We'll also set the kernel main to debug log, because that's where we are right now. I think it's just kernel main. What we expect to see is that we get a log saying we don't know the Ethernet type of the packet we just received, but only for the second one. And so we see debug logs here. We actually don't see any debug logs for main. It's possible that kernel main is wrong here. It might just be kernel. Yeah, so here we see parsing ARP packet and then found an unknown packet type 2048. And it's kind of bullshit to use 2048 here because all of the references are in hex. So here we should just format this as a like hex string that's like padded with a few zeros. So I think this is right. I think I say %6. I say like give me 6 leading zeros because of how do I say this? Because the 0x prefix, and we want 0x plus 4 digits. So I think it's like this. 0x6. Cargo run. We run test. And yep, here we go. We said found unknown Ethernet packet type 0800, which is IPv4. Solid. Okay. So we've got ARP. And now apparently I forgot a layer. There's IPv4. So before we get a UDP packet, we have to say implement IPv4 parsing. And what goes in here? So this should be pretty straightforward as well. There's probably just a frame here that we get. And I assume that the payload of this comes in after. So actually what we can do is we can look at Wireshark here and we can look at what he says the data is. And then once we parse, we can confirm that we get the same thing as Wireshark. Bing, bang, boom. We've got an IPv4 packet parsed. So let's get back in here, get back into main, start cracking at it. So we'll do the same thing we did before. We'll just wrap a byte string or byte stream, byte array, byte slice, however the fuck you want to call it, and we'll call this a UDP frame. No, IPv4 frame. And we'll like add getters to this that pull out the interesting data that we care about. So let's just look at this. Probably since we don't know what the fuck is going on, we can probably get away with skipping everything except for the protocol. So let's just do this for now. We'll take out the function of the protocol. And this is just a 8-byte thing. 8-bit thing, sorry, 1 byte. And this is just packet 9, right? We have 0, 4, 8, 9. Okay, and this will crash if this is not at least 9 bytes long, but we're not dealing with that shit right now. We're not worrying about it. So we'll say that if the type is 0x80, we parse the payload as an IPv4 frame. So here we say IPv4 frame is the payload. What is this? IPv4 frame. And the payload packet is payload. And then I guess we'll just for now say, let's print out the IPv4 frame protocol. And once again, we want to print this as hex. So we put in like a number 06x for what we want here. I guess it's number 04 here because it's only 2 bytes. Or 1 byte, not 2 bytes. Okay. So we run this, and now we get an info log somewhere. Writing packet with length, parsing ARP packet. Here we go. 0x11 is the protocol number we got, which hopefully lines up with UDP. Boom! Look at that. Very, very nice. So this was at 53 minutes in the stream, or 54 minutes more like. And so now we have a way to pass that on. So we've got our IPv4 frame, and we actually need to extract the payload from the IPv4 frame. So I think I can assume, based off what I've seen here. Sorry, where is it? So is this a 56 byte offset? Do I just offset 56 bytes in? Let's see. So if I look at this, this is hex. This is 8, 16, 24, 32. Sorry, 8, 16, 24. Is that right? No, sorry. 8, 16, 24, 32, 48. So my payload starts before 48, if I'm counting correctly. So this would be 0x28-ish in hex. Let's just check that. Python 3, 0x28 to, I think it's 0x30 is 48 bytes in. So, very interesting. That's not at all where I would have expected. Oh, sorry. Let's double check this. UDP starts here at hex 22, which is 34 in. So again, an interesting thing. Let's look at, so this says we have options if IHL is greater than 5. So let's see if our IHL is greater than 5. Is that what it said? It said if IHL greater than 5. So that's this guy. Header length. Oh! This says 20 bytes. So how does it know? So I must have made a mistake here, right? The fact that the UDP frame should start at 20 based off of this header length. Am I high? Oh, the IP header starts here. So it is 20 bytes off from here probably. Yeah. So this contains the minimum value for this field is 5. Okay, so right now we'll just assert that it's 5 because that's the only thing we know how to handle. Or maybe asserting that it's 5 is wrong. We'll say, we'll look at the header length field, which is going to return us a U8. This is the first value, but only the lower 4 bits. So we'll say get bits. And we're going to take 0 shift, I think, or are we taking the higher 4 bits? Let's see. Where'd it go? So this is the higher 4 bits. So we take the 4 of the higher 4 bits. We do need to include our utility class to do some bit manipulation. So let's just do that, which is the get bits trait. This. And now our payload should be self IHL. We'll just say assert equal self IHL 5, right? Because we are not handling anything else. And then if IHL is 5, IHL 5 equals 20 bytes, I believe is what this said. The minimum value for the field is 5, which indicates a length of 5 times 32 bits equals 160 bits equals 20 bytes. Oh, so we can actually don't have to do this assert shit. We can just say self.ihl times what is this formula again? Which yields a length of 5 times 32 bits or 4 bytes. So we'll say length is, we'll say the IPv4 length is this. And then we can just return self.packet IPv4 length. ... Right? Now, doing this blindly like this is fucked, right? Because what that means is somebody could just write in any number that they want, and we would like crash our kernel because we tried to index past the end of valid memory. But this is still a much better case than in the C case where we just access invalid memory. I would rather that, but in reality, we shouldn't do this. So we can try to fix me validate length here. But we'll assume for now that everybody's playing nice with us. That is the assumption we want to make. So we'll say let UDP frame equals self or IPv4 frame dot payload, or I guess we'll say here we have to actually match on the IPv4 frame protocol. And once again, we'll do this like if we have UDP, we'll do this, and we'll say in debug parsing UDP frame. Otherwise, we'll say unknown IPv4 protocol, and we'll even say what it is just for funsies. Are we chilling? Okay. And then maybe we print the UDP frame in debug mode, and we can start comparing with Wireshark to see if that like matches up what we want it to look like. Okay, so we send a test. We say that we're parsing the UDP frame, but we forgot to, we print lined it. So the UDP frame, we're just going to get some bytes somewhere printed out here, and that's annoying. So maybe we can say, here we'll say UDP frame is this. We'll run it, and here we see the UDP frame starts with 127001, which is not correct here at all, right? Here we should see the UDP frame start with B4 771740. Oh, sorry. Unless we're looking at the wrong dump. Yeah, we are off. So where is that 127001 coming from, actually? Oh, I'm sorry. I should be printing this as hex, or else it's hard to tell the difference. Because this is printing in hex in Wireshark. So the UDP frame actually starts with 7F001. That makes more sense. And we are a little bit behind there. So we've actually fucked up. But the header length does say that it's 20 bytes. 5 times 4 is 20, which should be what we calculated. So then the question is it lying? Right? Because the UDP frame starts here. The IPv4 frame starts here. So let's just count this out. So this is 16, 17, 18, 19, 20. Okay. So that should be right. That 20 does seem reasonable. Let's see what we've calculated for the length. So we can say that the IPv4 length is IPv4 length. We'll run this again. We'll punch in a packet. We'll say that the IPv4 length is 16. So that's a problem. So we are just using the wrong value here for IHL. Right, that's what that means. We're getting a 4 instead of a 5. So maybe we actually were supposed to grab the lower 4 bits, not the upper 4 bits, because network order maybe is backwards or something. Let's take a look at this again. So IPv4 header. Hello, IHL is 4567. But the version should be 4. So I'm getting this backwards in some way, which is a little concerning. Very concerning. Maybe because I have to do some big endian, little endian conversion, but that doesn't make sense. This has nothing to do with endianness. This is just the bytes. Well, let's just see. We'll print packet 0 is print in hex, and we'll print out self.packet0, and let's just take a look at what we see here. So we see, what the fuck? Why is this right now? This says IPv4 length 20, but it said 16 last time. Oh, because we stopped shifting. Sorry. We did fix that at the same time. So the packet is 4 on the high 4 bits and 5 on the low 4 bits. So that's weird to me. That means that the card must be like switching the byte, it must be inverting these. Which is a little scary. But that's okay. That actually makes sense maybe if we like read this byte by byte and like this is network order instead of normal order. Okay, sure. So we'll just put a note here. Putting a note there seems kind of crazy. Seems a little odd. Maybe if every single note, if everywhere we work with, we have to put a note for every bit shift, maybe that doesn't make sense. Maybe it's just like a prerequisite. Maybe we put it at the top of a file somewhere later. So we'll just say fix me. Note somewhere that bits seem to be reversed from network card. Okay. So now, if I run this again, or I guess we had the UDP frame should start with B477. And we do see that, B477. Right, we see that here. Very cool. So we're getting close. We have an IP frame. And now we just need to parse the UDP frame. Very nice, very nice. Which makes me wonder, what the fuck was I doing in the last 10 minutes? Because I said I already done that, but it's okay. We'll ignore that for now. Okay. So we have this UDP frame. And we've got the payload from the IPv4 packet. Very nice. And so now we just have to do the same thing where we have this like IPv4 frame, and we can do the same thing for UDP frame. So we'll call this UDP frame, and we'll create an implementation of UDP frame that extracts the interesting data for us. And really, for now, all we really care about is the payload, which I think we're calling it data here. And this, let's see how we are supposed to parse this. We get the length field. This guy knows that the payload is 5 bytes. So where does that 5 bytes come from? Let's look up the UDP frame on Wikipedia. So here he takes in, consists of a datagram header followed by a data section, the payload data for the application. The UDP datagram header consists of 4 fields, each of which is 2 bytes. This specifies the length in bytes of the UDP header and UDP data. Gotcha. Okay, so we get the length, right? We say function length is the packet at offset 4 to 4. And we say U16 from big endian bytes is this guy, right? And this is the length, right? And what doesn't he like here? I have to probably... I have to do try into and say expect U16 packet size incorrect or something. Right? This is like, it's okay to use expect here, because if this slice was the wrong size, then that would be like a programmer error, right? I would have had to put in a different thing than 2 bytes. And so I'm okay with saying that this isn't like an error thing. This is just like a programmer error type of problem. Now we can say we get the length minus 16, and we'll say that the header length is 16 is a U16 equals 16. Or I guess it should be Yeah, it's fine. Self length minus header length. And we say that this is going to be the data length. And now what to do is we say we have the data offset is the header length. So we say, just say self packet header length to, oh, we don't even need to do data length here. We can just do self.length as usize like this, because the header length, the length field includes the header. Right, so it's just like this. And this guy should be a usize as well. Okay, so now we've got all the pieces in to let us just print out the data here. So we'll say info received UDP message, and this is just going to be UDP frame pay data, and this we're going to convert this into a string. So we'll say chorister from UTF-8 unchecked. Now that's unsafe, but it's okay because I don't actually care. And we're missing the data frame on here because we need to convert this into a UDP frame, which comes from this guy. Very nice. Okay. So let's see here. Now, when I send in, when I run netcat here, I should be able to say like ASDF, and we should get ASDF, except we have fucked up. We have fucked up indeed. So let's go back. It's so what we're seeing here is that we're getting a slice index starts at 16 but ends at 13. So we're seeing this this guy is like totally wrong, and it's because I've just fucked up here, right? Saying that the header length is 16 is just like a fucking lie. It's 0. This is 2, 4, 6, 8. It's half of that. So we'll run it again, and we'll start spamming shit in here. And we see here, we received UDP message test. And let's try hello, Mick. This is a UDP message. Look at that. Isn't that sick? Oh, that's so cool. We did it. We did it. Yeah. Very, very nice. We have now received a UDP packet from my host operating system, and that means that we could start actually trying to do interesting shit with this, right? We could maybe try to like take in a packet that like sets the time, and we could use that to how do I say this? We could use that to change the RTC, or we could do something like if I type exit, shut down the kernel. If I type shut down the kernel. Right, just as like a proof of concept that we can interact with the rest of the system and do certain behaviors based off of what we get in these packets. So let's actually do that. So first, let's do a cleanup. Well, I guess first we'll flag that this is done. So we'll say this is finished at 1:13:58. And now let's say clean up my mess. And once we have like a UDP system figured out, then we'll start like trying to implement something interesting, like a shutdown or something. Okay. So I guess we'll just make like a network file for now, and we'll include it. So we'll say modnet, and all of this parsing shit should go in there. So that is all of this, the ARP stuff, the Ethernet stuff, the IPv4 stuff, the UDP stuff, the CRC stuff, all of this just comes into here. We'll copy our imports in just as a way to like get stuff compiling, and then we'll let the linter tell us which ones we don't need. right? So all this will work now. And now in here, we also have to replace all of this with like a parse packet. So we'll say function handle packet. Is that really where this belongs? Really, like the current, we're going to require a bunch of like kernel info from here, right? So where does this go? We like get this packet in, and we have like stuff that we want to do with it. We have these like multi-layer nesting of like packet type parsing. So it's like first we get the frame, the Ethernet frame. Then from there we determine if it's like an ARP or an IPv4 packet, and then the IPv4 packet we determine if it's a UDP packet or something else. And if it's a UDP packet, then we do something interesting. So what does this look like in terms of like function layout? We could start with like a free function that takes in the Ethernet that like dispatches to different subsystems. So the question is like who owns what? And it makes sense for the network module to own Ethernet parsing. And maybe it makes sense even for it to own ARP parsing. And it makes sense for it to own UDP parsing. The only thing that doesn't make sense for it to do is like parse the data of the packet, right? We are okay with it getting up to the UDP data and returning some structure. So probably what actually makes sense here is we'll make like a type that's like what we're going to return. So we're going to say parsed packet is just going to be like a sum type, right? And one of the things that he can be is a ARP packet. Sure. And this will take in like an ARP frame like this. And so we'll say like this. And then the question is like, does it make sense for the ARP frame stuff to get propagated up? I was going to initially say that we could like return an ARP frame if we needed to. But really that doesn't make sense because we can handle all of that internally, except for the fact that we don't own a way to write back to the network. Okay, so this seems reasonable. So we'll try to get an ARP frame, and in the parent, we will like construct our ARP response, maybe back in this module, but like the piping will be handled in our callback for now. And then this could also be like an IPv4, and this will be an IPv4 frame that also is for the same lifetime. And then in here, maybe do we want to handle like IPv4 and UDP like separately? Do we want to dispatch a second parse IPv4 packet? That seems pretty reasonable to me. So maybe this parsed packet name will have to change. We'll figure it out. Okay. So we'll write our function that's called like parse packet. And he returns a parsed packet. Right? And he just gets like a string or stream of bytes as his input data. And okay, so the first thing he's going to do is he's going to do this. He's going to get his Ethernet frame. And he's going to do this as well, where he gets the payload. And depending on the type of the payload, he's going to do something different. So this is the ARP side, and this is the IPv4 side. And then we have like this like other side, like this. We have a bunch of like curly brace fuck ups, so let's just fix those. And here we go. Okay, so here we'll say unknown. and we will return maybe the packet type in here, which is a U16. And so here, instead of logging, we just return parsed packet unknown t. For an ARP packet, we return ARP frame packet is the payload, and we need to now flag this as a parsed packet ARP. And we do the same thing down here for an IPv4 frame. Okay, and here we'll turn this to mute. And we're getting close. Okay, so now we parse the packet. So what does that look like in main? We say let packet is this is going to be let packet is net parse packet. Like this. Right? He doesn't like that that's a private function, so let's just take a quick peek there. This should be pub, not async. Oopsies. Okay, so now we don't need to worry about this like Ethernet frame parsing stuff. We can now just, we can now match on the packet itself, right? And here we're gonna have ARP. Hold on, it's we need to use net parsed packet, so we import this here, make this public, and in here we use create net parsed packet. We match on the packet, we get parsed packet ARP, and we say we'll use ARP frame here. And then the rest of this is actually pretty similar. So here our response is going to be a copy of the other frame. So here, I guess, we start to get a little tricky because we were using the internal details of the ARP frame before. But that's okay. We shouldn't actually be doing that. And instead, what we can do is we can do the same thing that we did when we generated the Ethernet frame. We can generate an ARP frame that matches. So here on our ARP frame stuff, previously we had all these like mutating methods. Fuck that noise, right? We just won't do that anymore. And just like we had a generate Ethernet frame, we'll just have the same thing for an ARP frame. We'll just say generate ARP frame. And this is going to take the ARP frame params, which is going to look like ARP frame params, and he's going to take in like a lifetime probably, because the parameters are going to have some maybe references in them. Let's take a look. ARP, 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 like a seal. ARP protocol. No, wrong one. No. Address resolution protocol. Okay. So here our inputs are going to be all of this. So we have hardware type, which was a U16. We have a protocol type, also U16. We have hardware address length, which is a U16, or a U8, I should say. Protocol address length, which is a U8. And operation, U16. Sender hardware address, which is a U8 of 6. Sender protocol address, which is a U804. And we have the same thing, but for S sender target. Very nice. So now we do the same thing here where we just, we make our capacity, which is just the size of an ARP frame params. But I guess that since this isn't packed, we actually have to do the calculation. So this is just going to be 28. Const ARP length, we'll just make this a U size and specify it here so that we have like a named thing to associate with this. Very nice. And now all we do is we just do the same shit we did before, where we basically just, it's actually very simple. We actually just extend from slice all of these. So we make a macro, we say ret extend from slice params dot this thing, and we actually probably want this to be a slice like this, so we do this for all of them, and then it's going to bitch that some of these aren't correct, so we'll say 2 BE bytes on all of the ones that are problematic. Very nice. All done. Okay, so now here, instead of doing this, we'll generate an ARP frame. So this needs to be public. And this will say net generate ARP frame, and we'll need to pass in the ARP frame params, which needs to be public as well. So we'll just quickly make this a public type and make all of these guys public as well. Very nice. And now we just need to generate these correctly. So let's import this type here. So this is in net. What the heck? This is going to be ARP frame params. We have to put these in here. So this is a borrow now, and now it's going to bitch that we're missing a bunch of stuff. So let's look at the ARP frame and make all of these functions that like grab information about it public. One sec, this guy. Okay, so hardware address length. This is 6. What else is it missing? Hardware type. This is just going to be the same. Actually, we should just mirror everything in the request. So we can say that hardware type is the ARP frame.htype. And this guy actually needs to be a U16 now. And this can be from BE bytes. Or it's actually U16 from BE bytes like this. And then we get into trouble because this guy needs to be like in try into dot unwrap this, and this doesn't have to be unwrap. This can be expect because this is a reasonable problem. It will just be like if this was not possible, then it would be because that the slice is not of size 2, and that's obviously incorrect. So we will say invalid length for H type. Okay. Now, p-type, we're going to do the same thing. This returns a U16, and this is instead of 0 to 2, this is 2 to 4, and this is p-type instead of h-type, which means that here we can start punching this shit in again. So we have hardware type is h-type, protocol type is ARP frame p-type. We're missing hardware address length, which is going to be the same, so ARP frame dot hardware address length. We have the protocol address length, and that's going to be the same thing. We're going to copy it from the original request. And now we're missing operation. This is operation 2, I believe, for response. 2 for reply, yep. And we're missing the sender hardware address, which we previously had in here as MAC address, like this. And the target hardware address is the requester address. So we have arp frame dot sender hardware address like this. Okay, so this guy needs to be this returns a slice for the hardware address, so we'll just pack him into a like a 6-byte array here. And we'll say that the input address length wrong or something like that. And now we're missing sender protocol address. And this is going to be, we're kind of like saying that no matter who asks, we respond. Now that's like technically untrue. Right? So maybe we should put a fix me in here and say we shouldn't claim to be all IPs. But for now, that's fine, right? We're just trying to get shit working. Try into, and we expect, and we say, we assert basically that the protocol address should be 4 bytes, like this. And now it's missing target protocol address, which is the same thing here, except instead of using target here, we use sender. Okay. And now we delete all this shit. Oops. Very nice. And pack that into the Ethernet frame. Very nice. And we just have to make sure that the Ethernet frames type is public now because we've moved it into another module. So this needs to be public, and this needs to be public, and all of this shit needs to be public, baby. There we go. Cargo check. Now we're getting close. There's probably a bunch of other shit that's wrong here. So this needs to be imported just like the ARP frame params did. The Ethernet frame params also need to be imported. So here we have Ethernet frame params like this. Very nice. So now we need to check the other types. We have parse packet IPv4, and we'll call it IPv4 frame. Okay, we are getting closer. The destination MAC here should be the ARP frame sender hardware address. MAC address here, and the payload is the response here. We borrow it because we don't actually need it, and we don't have source MAC on the ARP frame. This is a sender hardware address like this. Okay. This is already looking a lot better. That, instead of like jumbling a bunch of shit, is just a couple little complicated function calls. This will also have to be moved into the net function eventually. We have the IPv4 frame now. And here we have to give him the same treatment. So we maybe parse the IPv4 frame manually and get out a UDP frame. So let's try that. Maybe we split this way so we can fit more on the page. So in the same way we have parse packet, we'll have parse IPv4. And inside here, we will take in a frame that is a IPv4 frame. Right? And he has some unknown lifetime that we don't really care about. And our response is an parsed IPv4 frame. And a parsed IPv4 frame is just going to be a UDP frame, which is going to have a UDP frame inside it, or unknown, and we'll have a U16 for the protocol address. We need to stick in some some A's in here for lifetimes to match them together. And we need to inject a lifetime here to make Rust compiler happy. And now, instead of doing the Ethernet frame, we can just say frame.pay, or what methods do we have here? We have protocol, and here we have this guy. This guy should actually just be this, right? Delete this. And here we return parsed IPv4 frame unknown with the protocol type, which is actually U8, not U16. Or we return this UDP frame. So we say parsed IPv4 frame UDP and return this guy. Very, very nice. And we actually have to match lifetimes here because they're tied together. And here we don't have to take the frame. Let's just say frame and frame. This also is frame. Okay. So now instead of this, we say let UP frame. Oops, we'll say let frame is net parse IPv4. We pass in the IPv4 frame like this. We pass it in as a reference like this. And now we match frame and we say if we get a parsed IPv4 frame, parsed IPv4 frame UDP, with the name UDP frame, we'll do the same thing here where we'll print this. Like easy. And otherwise, we'll return the unknown. We will do this same log we were doing before. We're pretty close now to being able to just run all of this refactored code. So we just need to fix a couple lifetime and like module issues. The UDP frame needs to have some public methods, so we'll just call the only public method data for now. And unknown is we spelt it wrong here, unknown. Unknown. And this guy also needs to be unknown, not uncone. And this also has to do the same parsed packet unknown. We need the same treatment here. Okay. Do we compile? We're close. What we're missing? That the logger type, when we copy this in here, is needs to be create logger. And we have a problem here where this needs to be mutable, but it doesn't need to anymore because we're not mutating it ever, so we just take the mute out. Right? Here we have a borrowed thing that can't be borrowed. So we actually have to tie the lifetimes together again here like this, I think. Maybe not. Why doesn't he like that? It's because frame is a local type, but the frame payload should have the same type. So we can actually just, we should return a payload. The payload should be attached to the frame. Yeah, to the frame. Nice. So we can just like wiggle some lifetimes around and that makes it okay. And we need to give the same treatment to this IPv4 thing, where the payload in here needs to be tied to like the packet lifetime, not my like own lifetime. So we give the same treatment, and this guy needs to have a lifetime specified to 0 as well. Okay. So now we have some more like public-private shit to do. So this needs to be a public thing. This needs to be a public thing. And this, oh, we actually might be good. Card check. Nice, we compile now. And if we run, do we see the same shit that we saw before? Do we still work? And no, somebody's unhappy. Packet too short. Interesting. Interesting. So whoever sends this guy? Packet length is less than 64. Aha! So probably we made a mistake in our like Ethernet frame generation. And so let's take a look at this. So we probably just need to 0 pad this. So probably here we say length is the minimum of this, or the maximum of this, or the 64 minimum. And here we'll say, or no, here, we'll let the length, we'll calculate the length, right? And here we'll add, so we'll say if the length of this guy is less than 60, because we have 4 bytes left for the slice and we need 64 at least minimum, here we'll pad this to match. We'll say if the length is less than 60, we'll just set the length to 60. And this should not be set random, this should be resize. And we have to pass in the value that we'll shove in there. And we'll just 0 pad, so we'll shove in some zeros. And fix me named constant. We'll handle this later. And let's see if that helps at all. It does. Okay, so very nice. If we look at Wireshark again here, I bet we will see something saying here. We see our input thing, our output thing, and then our receive packet. Very nice. So that's some good like initial cleanup. I think I will probably keep going along these lines where we move the parsing into network. Right, we need to do a little bit more here where this is a lot better than it was before, but probably this whole callback should live in the network space. And it'll just be kind of more of the same where we like iterate on pushing stuff farther down so that our packet handling stuff looks cleaner and cleaner. But I think I'll probably do that off screen because it's kind of fucking boring, right? And what I will do now is I'll just do this last piece here where if we get a UDP frame, let's see if we can do something interesting like just quit. So let's just say if UDP frame data is equal to exit, we will shut down. Right? Easy. Cargo run. And now what we should do is we should say test, 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 exit. Very cool. Very, very cool. And is there anything else that we should do in there? No, I think that's all I really wanted to get done. So thank you very much for watching. If you want to catch me live, I stream most days at around 2 Pacific time. And the Twitch link is in the YouTube description. And if you're watching me live and you missed something and you want to catch up, you can always go to my YouTube, which is linked on the Twitch. Thanks for watching. This is a good one. I'll catch you on the next one. Bye.